Okay, so good afternoon, everyone. Today we have a real honor and privilege to welcome with us Professor Malik Maaza. Professor Malik Maaza is a UNESCO UNISA Africa Chair in Nanoscience and Nanotechnology, and is also an extraordinary professor at the University of South Africa. Today is going to talk to us about artificial intelligence and machine learning for material discovery. And we will circulate the CV of Professor Maaza so you can see the extent of his work and interest and also awards. He's been in many countries, has many achievements. So, Professor Malik, the floor is yours.
Thank you so much, Professor Muriel, and General and Senior Fellow. Thank you so much for giving us the honor to attend this talk. What I would like to do, if you allow me to do so, let me just switch. Yes. Let me just share my screen with you. Yes. So, sorry. During this talk here, I would like to share with you some of our experience in terms of material science, but and their potential applications in a number of fields, such as water purification, such as energy storage, such as designing and advancing the type of nanofertilizers and so on. So that this talk that I'm giving is within the framework of the UNESCO, UNISA, ITAMBA Labs, NRF, Africa Chair in Nanosciences and Nanotechnology, and it's a really special honor to share this talk with you, because behind this UNESCO Africa Nano Chair, initially the architect of this chair, it's no more or less than the Abdusalam ICTP in Trieste, which is of course associated to the East Africa Institute for Fundamental Research. So it is a privilege and a special honor for us to share with you this talk. This UNESCO Africa Nano Chair is in effect a trilateral partnership between the UNESCO plus Fontenoy in Paris, the University of South Africa in Pretoria, as well as ITAMBA Labs, which is a national facility of the National Research Foundation of South Africa. And this chair, in effect, reports back to a number of ministries: the Ministry of Basic Education, the Ministry of Higher Education and Training, as well as the Ministry of Science and Technology and Innovation. And this UNESCO chair is a network of excellence of the African Union, and it's the sole UNESCO chair in the South, and we are glad that it is in Africa. The mission and the vision of this chair is, is the training of postgrad students in the field, or in the multidisciplinary field of nanosciences and nanotechnology. And as you can see, quite large cohort of MSCs and PhDs were trained in our labs, and among them Agnes here from Rwanda, and many from Rwanda in effect, but other parts of the African continent, as you may see. Also, within the framework of this chair, the gender aspect is of a pivotal importance. And as you can see, these young fellows here from different parts of the African continent, including some colleagues from Brazil here, In effect, all of them were winners of the L'Oréal UNESCO Award for Women in Science, just to highlight how robust and how committed are these fellows when it comes to nanosciences and nanotechnology. Of course, the training is not limited to MSCs and PhDs, but also to postdocs and early career scientists from different parts of the African continent and beyond the border of Africa, such as here in the case of the doctor in Yemen, other fellows from Middle East, and so on. So these fellows embark in multidisciplinary research involving material science, but while the core component is material science, the computational and the modeling is of a pivotal importance. And the contribution of material science and computational have quite a number of applications and synergies with chemistry, with environmental, ecology, agriculture, and health in general. And of course, engineering. The fellows, postgrads, MSCs or PhDs, as well as a postdoc and early career scientist, they embark in engineering advanced materials with the target. A target is an application with one of the SDGs, being it SDG 6, water, being it SDG 3, that is health, or being SDG 7, that is materials, advanced materials for energy applications. And as you can guess, if we have to go through a standard way whereby we synthesize some material and when investigate its all properties by changing the concentration, by changing the nature of the alloys and so on, it would take a lot of time. So the idea or the ideal approach is to embark in computational, data mining, machine learning, and computational to identify the ideal pathway to engineer an outstanding and multifunctional material which would have the requested properties for an application in water, for an application in health, for an application in energy, and so on. And as I have mentioned, fellows and colleagues, if one has considered the Mendeleev table, if we have to, how can I say, the 63 elements of the Mendeleev table, if we have to combine all of them, the number of combinations with the minimum of energy is infinite. So it is not possible, how can I say, just to embark in a try and test and a try with such a classical standard approach. It is just practically impossible. Therefore, computational and modeling using standard modeling softwares and so on and tools such as the DFT, density functional theory, or molecular dynamic, at least the basic ones, it is possible to predict more or less the ideal materials. In addition to that, using machine learning and data mining, in addition to artificial intelligence, it will swiftен and prompt more or less the way and facilitates more or less the way to go to engineer the ideal materials for application X, Y, and Z. And in this regard, I would like to share with you some typical examples which have really allowed us to make really a breakthrough, while yet indeed we have a minute amount of capabilities relatively to our colleagues in the north. And in this regard, I would like just to embark in SDG 6, that is clean water and sanitation. You would understand in this typical example is that water scarcity and water quality is of a concern somehow. Here, just to give you an idea, these are the predictions of the World Council of Water, as well as the United Nations Commission for Africa, UNICA, when it comes to water availability and scarcity. So here, for example, in the blue science, you have the availability of water in 1990, 1990. That is the availability of water, as you can see. Now, in 2025, that is last year, the level of water is given by the dark bars. You would see that before, quite a number of African countries, they were above the vulnerability level, and many of them were above the stress level, as well as scarcity level. But as you can see, in 2025, last year, a number of countries are under vulnerability level, or nearly all of them are under vulnerability level. What does it mean? Vulnerability level. That means there are some communities who would not be able to shower, who are not be able to use standard water to clean. Others have. But when you are under vulnerability, which means that quite a number of communities will not have a possibility to clean for hygienic from hygienic aspect, but a number of countries will be under scarcity, as you can see. What does it mean? That means that some communities will not be able to have access to drinkable water. Therefore, the water that we shower with and so on, and the water which is contaminated in the agriculture fields and so on, the groundwater must be cleaned and must be treated to correspond to the demand. Because the rain rate and the rain ratio has decreased extensively, diminished. So we need to clean water which is used in the agri sector, in particular the groundwater which is contaminated by pesticides. And in this regard, we have to devise materials which are capable to clean. And the material of a choice is the titanium dioxide. The titanium dioxide is a whitish powder that is mixed to a coagulant, which allows you to have to clean your teeth with a teeth brush. Also, the titanium oxide is that formulation that you put on your skin when you go to the beach to protect your skin from the sunburn and the UV radiation to protect your skin from cancer melanoma. It happened that this TiO2, this titanium dioxide, is very effective when you irradiate it with the UV radiations. But unfortunately, the UV radiations in the sun, in the solar spectrum, is around 5%. It's not much. So you cannot use this TiO2 to clean, to decontaminate water from bacteria, from pesticides, and so on. But generally speaking, we use the titanium dioxide particles in water, in contaminated water, and expose that water to UV radiations, and the UV radiations interacting with the electrons of the external particles of the TiO2 creates redox compounds, and these redox compounds attack and decompose any bacteria in the contaminated water or any pesticide in the contaminated water. Unfortunately, this technology is adapted to north countries. It's expensive for the south because you have to use a UV lamp, and a UV lamp is extremely expensive. So the idea is to design TiO2, titanium oxide particles, which are sensitive to solar light, not to the UV, but solar light, that is yellow, the white, how can I say, the green light, the yellow light, and so on and so on. So for such, you have to find out that in effect, what you should do, instead of embarking, trying to try and error and so on, when you do, how can I say, DFT, density functional theory, and molecular dynamic, you will find out that if you create surface defects, oxygen surface defects of the normal TiO2, you will make it very active to solar radiations. Not only UV, but solar radiations. And it's there where it's free. The sun, how can a sun has more than 30% of its, how can I say, more than, 35% of its radiation, it's in the visible range. So therefore, this titanium with the oxygen defects on the surface will be active to solar radiations and not to the UV specifically. And as you can see, the density functional theory shows us that you can reduce the band gap from 214 to nearly 0.039 electron volt. What does it mean? That means while the TiO2, the standard one, the white one, is active only under UV radiations, the same titanium dioxide, but with the defects on the surface, due, how can I say, as predicted by the modeling, DFT and molecular dynamic, it will be active in the visible range, and that is the case. Here is the black TiO2, and specifically this one. These particles are very, very small, extremely small at the nanometric scale. And if you take this black powder and you put it in a tube of water contaminated with pesticides, you would see that this water contaminated with the pesticides, initially it was blue, and after exposing it for a half an hour to the solar radiations, it becomes less blue, and after 2 hours time it becomes nearly transparent. What does it mean? That means that black powder that you can see on the bottom here of the tube, this black powder, with its reaction with the sun, has decomposed the methylene blue molecules, which is the harshest equivalent of the harshest pesticide. So you can see clearly that here the modeling and the data mining, machine learning, as well artificial intelligence, allowed us to find out a way to a cheap way, a very clever way, a very effective way, but cost effective for the South, for Africa in particular, to decompose and treat water, contaminated groundwater. This is a typical example, of course. The second one, it's related to health. One of the major problems of, how can I say, contamination, as you can see, these are dots, red dots, and these red dots shows how much, who are the countries who are heavily contaminated with arsenic. And this arsenic does not come from manufacturing or industry. No, it is geoleaching. It's coming from, how can I say, from rocks and so on. Groundwater, when it goes in, how can I say, it brings with it arsenic. And this arsenic is extremely toxic, in particular to the babies in the womb of their mothers. It can be extremely effective in destroying the neuronal capabilities of the baby and of the fetus. Of course, it has quite a number of effects on adults, but as you can see, this arsenic is all over the world, not limited only to the south, but all over. You can see in the case of Ghana and so on. In the case of Ghana, Cameroon, and so on, quite large because there is artisanal mining of gold, whereby they use mercury and arsenic-based materials to treat gold deposits. But nonetheless, there are quite technologies to clean water, but these technologies are extremely expensive and are not fit with the needs and capabilities of the countries in the south and Africa in particular. So we have had to come with an approach for such. And it happened that the DFT and the machine learning as well as data mining informed us that in effect the ideal material, the ideal compound that can catch easily arsenic is sulfur. In addition, machine learning and data mining allowed us to find out that the sulfur can be bound easily to copper. So we said, therefore, let's try to sulfurize copper surface, and let's try to have it in, how can I say, nanoscaled. Well, that is exactly what we obtained. As you can see, here is a surface of copper which has been sulfurized. If I tell you how we have sulfurized it, you will laugh. You will laugh. Why is that? If we have not used such approach of data mining, machine learning, and artificial intelligence, we would never thought about it because, how can I say, nobody will think about using garlic. Using garlic to sulfurize the copper surface. Why is that? Because the copper has a large and high concentrations of sulfur-based phytocompounds. And these sulfur and phytocompounds are very, very effective in sulfurizing the surface of copper. And that's exactly what you see here. You think it's something like a coral in the sea. No, it is a surface of copper sulfurized using the phytocompounds of garlic. And fellows, of course, this is a patent of a student and also publication in Nature. So as you can see, here is you take contaminated water with arsenic, a standard one, and you take your copper mesh, which has been sulfurized to have such a structure that I showed you before. That is this one. And it happened when you expose that standard solution of arsenic, after 24 hours, you remove nearly all the arsenic. Nearly all. And you are at the limit of, you are even below the limit of the World Health Organization, which is 1 ppm. And here you are less than that. So it shows clearly, fellows, that combining data mining, machine learning, artificial intelligence, and computational, it allows you to identify not only the ideal material to embark in, which would respond to your target, but also to, how can I say, gain in times instead of going for essay and trial and essay errors. And it happened that this material, when you go to run some additional experiments, you will find out that it is stable, and therefore everybody in the rural areas or in the, how can I say, in urban areas, you can use this approach to decontaminate water from arsenic. The example that I would like also to share with you, and this is a really very competitive, it is related to energy, and it's SDG 7. You would see that in effect, just to give you an idea, this is a thermograph temperature distribution of a standard house and a standard car. As you can see, the heat exchange between the atmosphere, the atmosphere and the house, and the atmosphere and the car is mainly through the windows. And therefore, how can I say, when it's hot, the heat goes through via the windows, both in the housing units as well as the car units. And when it's cold, the heat is lost from inside to outside, both in a house and in a car. And therefore, how can I say, in the winter we have to heat, and in the summer we need to use the air conditioner. And this, in both cases, we are consuming energy. Therefore, we are more or less contributing directly or indirectly to increasing the CO2 footprint. And you would see here, for example, this is a modern city in the Taiwan. You would see that in effect you have air conditioning in each of the flats, all. And this air conditioner, first of all, they consume a huge amount of energy, so they put the national grid under duress. One. Second is that to use them, they will emit, how can I say, that energy that they are using, it has certainly emitted a huge amount of CO2. So therefore, the idea is to come with a smart window. What is a smart window? A smart window, it's a window, glass window, which is coated or painted with the material, with a coating, and that coating must be smart. That coating should reflect the heat from the sun when it is hot, and it should allow the heat from the sun to go in when it is cold. And the heat from the sun are infrared radiations. So we need to have a coating which is smart to stop the infrared from the sun to come in when it is hot, and to be stopped to be reflected back when it is hot. And for such, you are obliged to identify this material. You just cannot guess and go to read all the books and all the publications and so on. You are obliged to use cleverly machine learning, data mining, machine learning, artificial intelligence, and come with the right material. And here, generally speaking, I will not go through the details, colleagues and fellows, sorry for the time is limited. So generally speaking, we can see that there are quite a number of materials which can be used for such, but the ideal one is a VO2. VO2, it is a semiconductor at low temperature, and it's metallic above a certain temperature, which what we call critical temperature. But this, how can I say, this temperature of VO2, all of them are not suitable except this one. Why? Because its temperature is close to room temperature, but it's still high. It's 68 degrees Celsius. What does it mean when it is metallic? VO2, vanadium dioxide, is metallic. That means it stops the heat. It stops the infrared. Any metallic coating stops the infrared. Any semiconductor material will allow the infrared to come in. It's transparent. So we are looking for this material, but we have to modify it. Well, so how can we do it? So we have to go for data mining, machine learning, artificial intelligence, and molecular dynamic, density, functional, and so on. And you find out that, oh, if you could, instead of using thick VO2 films, it's better to use the thin ones and so on. And when you do that, you are able to find the ideal coating. And that ideal coating, as you can see in this toy house, you can see that this house with the window without coating, and this one it's the same one but with the coating, the orange coating, as you can see. And here you are shining with the lamp, and this lamp is the equivalent of a sun. Its radiation, it's equivalent of a sun. And you have a thermometer inside. The thermometer, the temperature measured by the thermometer inside with the room with the window without the coating is around 42 degrees Celsius, while the other one with the coating is 33 degrees Celsius. It's nearly 10 degrees different. So you can see that in effect this coating is very effective. It stops the heat from the artificial sun, and this is how it was managed to come in with such a kind of a solution without wasting a huge amount of time, but coming with a solution for a green air conditioning. And you will see that this technology would be, these smart windows will come in a force. Why? Because with the increase of temperature of the globe, huge amount of air conditioner will be used. And this air conditioning unit, for the moment, they are more or less used by the most rich countries somehow, as you can see, countries who can afford, such as Mexico, Brazil, I think India, Singapore, and Indonesia, and South Africa. But the bulk of other countries will not be able to sell. Therefore, we have to embark in such a smart, green air conditioning. How can I say, the example of also how machine learning, artificial intelligence, and computational allowed us to come with a potential solution in converting the CO2 to functional material. All of us, we are aware, all of us, that the culprit of climate change is the carbon emission. It's the dioxide, carbon dioxide emissions. And as you can see, while the bulk of the countries are emitting a huge amount of CO2, Africa is really small, excluding South Africa. But Africa in general is small if one has to exclude South Africa. In addition to that, yet even if we are not emitting a large amount, quite a number of countries, including South Africa, Egypt, Algeria, Nigeria, Angola, Kenya, and Ethiopia, as well as Libya and Morocco, are emitting a huge amount of CO2. And the market of the CO2 in 2028 will come in, and therefore addressing this climate change, we needed to find a solution in converting this CO2 to something. How we do it? Machine learning, data mining, and artificial intelligence guided us on the fact that we should biomimic Mother Nature. Mother Nature transforms the CO2 to coral, as you can see. It transforms it to shell material. and it transforms it also to pills. So therefore, we have to biomimic, so density functional theory, molecular dynamic, and so on, and combined with the other methodologies, has allowed us to convert CO2 to this whitish powder. And this whitish powder is what we call carbonate. Instead of going, how can I say, to technologies which are expensive, energy consuming, well, machine learning, data mining, and artificial intelligence has showed us that we should embark in biomimicking Mother Nature. Therefore, Mother Nature does that, we do this, we produce this. And this material is an excellent fertilizer. As you can see, you can do high quality, top quality, world quality science published in Nature, but you can also demonstrate and validate that it can be used as an excellent fertilizer. As you can see here, this is a tomato plant. This is a tomato plant without our nano fertilizer. This is with a small amount. This is with the average amount, and this is with a high amount, smaller than the threshold of toxicity. And as you can see, the tomato with our nano fertilizers, that whitish powder which was produced by converting CO2 to a fertilizer, to a carbonate. As you can see, its efficiency here. Prof. Meriot, how much time I have still? Prof. Meriot?
Yeah, you have 1 hour, so you can talk. We started.
Okay, thank you.
We started late, so.
Thank you. So the
You're
last
welcome.
example that I would like to share with you is a concept of James Clerk Maxwell, the father of electromagnetism. As you are aware, energy can be produced from different sources, being it solar, being it wind, being it hydro, biomass, being it liquid gas, whatever, nuclear, and so on and so on. But in effect, what we do, half of this energy which is produced is used effectively, but half of it is lost as a heat. Nearly half of it is lost as a heat. And why is lost as a heat? Because our cooling fluids that we use to cool our centrals and our, how can I say, units of production of energy, they do not have sufficient capability to cool. And just to give you an idea, this is an engine of a car. When, how can I say, when you start your car, the pistons start to operate. When they operate, they consume energy and they emit CO2, of course. Nonetheless, this energy through thermodynamic cycles, which is generally speaking Boe-Rochat cycle, up to now is the Boe-Rochat cycle. These pistons, when they operate, they generate heat by friction, and this heat is removed by water, which comes from the radiator and so on. And at each cycle, the water removes a certain amount of heat from the engine, and it takes back it to once again to the radiator, and you have the fan and the radiator, you have the air coming in and so on. So it cools down that water, and that cooled water it comes again, once again, and for another cycle, it removes some amount of heat from the pistons, and it goes again another cycle. The point is that when you start from home, the engine of your car is cold. When you arrive at your working place, the engine is hot. Yet when you departed, the cooling system was operating. But unfortunately, your engine was not cooled effectively. Why is that? because the water, yet the water has the highest thermoconductivity among all coolants. Its thermoconductivity is low, is less than 1 watt per Kelvin per meter. As you can see, this is the thermoconductivity somehow of different fluids, organic materials and heat transfer fluids, as well as compared to metals and their oxides. You would see that all the normal coolant fluids, the thermoconductivity is less than 1 watt per meter per Kelvin. But the one of metals and their oxides, it's 2 to 3 magnitudes higher. So James Clerk Maxwell, the father of electromagnetism, has proposed that why not to put particles of metal, small particles of metals or their oxides in these fluids here, and because the thermoconductivity is an additive thermodynamic parameter, therefore if you add particles of this in this host fluids, you will increase the thermoconductivity somewhere here. But in his time, he took indeed powder of oxides and he crushed it. Unfortunately, when he crushed it and he put it in a fluid such as water or oil, it has worked at the beginning, but with the time, the particles that he has had in his time, they were very big, or microns. So gravitation pulls them down. But since 1990, we were able, or even since Faraday, we were able to make nanoparticles. When you make a nanoparticles, particles with a diameter in the nanoscale, just to give you an idea what is a nano, you take 1 meter, you divide it by 1000, it gives you millimeter. You take that millimeter, you divide it by 1000, it gives you micrometer. When you take that micrometer, you divide it by 1000, it gives you nanometer. So it is extremely very, very small. It is, if you take 10 atoms close to each other, of gold of 1 angstrom radius, 10 of them, they will give you 1 nanometer. 1 nanometer is 10 angstroms, is 10 atoms close to each other of a necklace. So you can see clearly they are very small. If they are small and you disperse them in a liquid, being it water or oil, the Brownian motion of this particle will take it over from the gravitation force, and therefore they will stay suspended, and therefore the theory of, or the concept of James Clerk Maxwell is valid, and therefore you create a new generation of what we call nanofluids. And these nanofluids can be created by different ways and so on. And one of the approaches that machine learning and data mining, as well as molecular dynamic, including CHPC and the computational, told us or informed us that we should not just go for a specific material. No, go for a silver nanoparticles coat on carpets of graphene. Graphene is a sheet of graphite. When you take a pencil, and you write on your piece of paper, what you are putting, in effect, what you are doing, you are removing sheets of graphene, yes, sheets of graphite sticking on your page, and that is graphene in effect. And that sheet of graphite has an extremely elevated thermoconductivity, higher than the thermoconductivity of a diamond. And if you decorate it with the silver in effect is the metal which has the highest thermoconductivity of any metal. So therefore, if the machine learning and density functional theory and data mining have not allowed us to go that route, we would not think about it. And here is it. Here at the first page is graphene sheets. Here are silver nanoparticles. Boom. And here is graphene covered by silver nanoparticles. And the thermoconductivity of it is, here is the ethylene glycol as a host material. You can see the thermoconductivity is around 0.33 watt per meter per Kelvin. But when you use silver anchoring graphene sheets, the thermoconductivity jumps by 33%. You would say, oh, it's just moving from 0.33 to 0.40. It's not much. No, you are wrong to think like that. Because if you are a thermal energy engineer and you see a thermoconductivity moving from this value to that value, it will tell you another story. A huge amount of an increase of 33% and a high stability with the time. And as you can see here, it was published in Nature Family Journals, as you can see, and this was done by students. Also, the applications of these nanofluids or a new generation of coolants is for solar energy. If you consider a photovoltaic panel, if it is hot, its efficiency is reduced extensively. If you cool it down the effectiveness is very higher. It is close to its theoretical efficiency. So using water which has a limited thermoconductivity is not ideal, but the ideal is using this new generation of nanofluids. Better than that, as you are aware, all of you are on your cell phones. All of you, all of us, in fact, not you, but all of us, we use extensively YouTube, TikTok, LinkedIn, name it. And all these capabilities and our emails which are on the cloud, all these modern tools and so on, they do use and they do require massive amount of data centers. And these data centers, they consume a huge amount of energy, and they release a huge amount of heat. And that heat has to be removed from these data centers. Just to give you an idea, this is what a data center consumes approximately between 200 and 250. See Nigeria, what it consumes, 29, Colombia 73, Argentina 124, Egypt 150. This is the energy consumption of this country for their own use. And here data center, it consumes more energy than countries. This is madness. And therefore, that heat generated by these data centers should be recuperated, and therefore necessity of using very effective generation of nanofluid of coolants, and therefore nanofluids. And by that, fellows, I wish to thank you, Azante Sana, Nkosi, and merci beaucoup, and shukran jazilan. Thank you so much, Program Director, Professor Miriot. I am done. Thank you.
Thank you very much, Professor Maaza, for this excellent talk and challenging us with in this world of material and finding the right one. So I will open the floor for questions. So any questions? So you can see our students, Professor Maaza, in the
Yes.
conference room, the master students, year 1, year 2, and some students, PhD students. So maybe Sunday has a question, given that he's working on machine learning.
Can I ask one? Oh, okay. Go for it, Sunday.
Yes,
Okay.
Sunday.
Yeah, thank you, Professor, for the presentation. And it's really interesting that interesting science is being done in Africa to take advantage of the materials that we have. My question is on the data mining aspect. When you say use artificial intelligence, machine learning, I wanted to know, do you search for already existing data sets that are available online for these materials that you have mentioned? Or is it like more of an engineering, like you try to modify properties of existing materials? So is it a search on an existing data set? And if it is a search on an existing data set, what are some of those data sets that you people have searched to be able to come up with these potential materials that you mentioned?
Thank you. Thanks a lot. In fact, what happens here is that there are quite a number of databases, and I can say first scan is to identify somehow what type of materials we are looking for, and the material that we are looking for is defined by the application that we are targeting. Once we have this link, we just go for standard literature review, and from the literature review somehow we embark in artificial intelligence. We use Grok, Gemini, whatever, just to give us what is the best pathway that we should consider. Once we have that, if I take the case of the vanadium dioxide or the titanium dioxide or the water, what we do is that we, how can I say, machine learning and how can I say, and artificial intelligence will give us more or less a broad range of, and we will see what is the one which consumes less energy for its engineering, for its product, for its fabrication. From that, we embark in a computational, and we find out that some materials are there. What we should do is just to create defects. We should just modify them, but modify them within the volume or outside. So it is in that regard that the complementarity between the different methods which would allow us at the end to make the choice. And this is what we should do. And we embark now to the lab once we have done this homework of literature review, both with artificial intelligence, guided also by the data sets and databases, and ensuring that their fabrication will require minimum of energy, minimum of water input, and so on. And it's not toxic and so on. It's biocompatible and so on and so on. So there are these different aspects that we consider, and we embark in that material. We go to the lab to try to fabricate it if possible.
Okay, so then my second question is on for photocatalysis. I believe the descriptor you use to search for the material is the banga. Is it the banga of the material?
Correct.
Okay, so what about for the conversion of CO2 to bicarbonate? What descriptor did you use in searching for the potential materials that you use?
Please, I would be grateful to you if you could just repeat your question.
Okay, so for the CO2 conversion to carbonate, what descriptor did you people use in searching for the potential material that you eventually use? For photocatalysis, band gap, what about CO2 conversion to carbonate? What descriptor did you use?
In the case of the CO2, we wanted to, how can I say, our approach was to say, CO2 is seen as a burden, isn't it?
Yes.
But the idea is to say, what if we consider CO2 as a raw material, as a beneficial material, rather as a burden? What we can do with it? So when you embark in artificial intelligence, machine learning, you say, I consider the CO2 as a raw material. Automatically you are guiding, more or less, you are converging towards a conversion of the CO2 using a minute amount of energy. So it guided us on the biomimicry, how the CO2 is converted to coral sea when it's absorbed in seawater. So initially, we were trying to find out what is this material that would allow us to convert the CO2. But our findings is to say that no. How can we convert, instead of looking for a material who would be able to convert the CO2? Our results guided us on the process of converting the CO2. And we found out that the coral formation, the coral has to create a skeleton. And the skeleton of the coral is the carbonate. How that carbonate is produced? That carbonate is produced by converting the CO2 and making it reacting with the calcium and the minerals in the seawater. So it is that process which allowed us. So simply said, it has not guided us on a photocatalysis. It has not guided us on a band gap engineering. It has not conducted us in breaking down the molecule of CO2. No, we have been guided towards reacting the CO2 with a material. And that material is any material contains magnesium, calcium, zinc, name it. This mineral, you find them in the seawater. And so is the CO2 molecule. So the process that we have found is that equivalent of biomimicking the formation of the skeleton of the coral.
Okay, can I ask?
Yes, go ahead.
Yeah, so I want to know the workflow you use in your search. Like you use artificial intelligence, like the large language models, ChatGPT to ask questions, and then it gives you a guide on what to do. Then you use machine learning to mine the data set. Then before you can now identify the possible candidates, and then you now go ahead to do further screening. Is that a workflow you people use in the search for your materials?
Correct. Once we have been guided, I can assure you that you can do this experiment yourself in the kitchen. Okay. Simply said, you take you take calcium chloride. Okay, you take a calcium chloride. Let me not, let me not take a lot of your time. The point is that initially, we were targeting finding a material which would act as a catalyst. We found ourselves far from that. We have been, our way of thinking has been deviated, and I have been told to go 180 opposite. So we went opposite. When we went opposite, we found out that it works very well. It's a minimum of energy, green, low toxicity, biocompatibility, and so on. And the CO2, higher is the amount of CO2, higher is the efficiency of this process of converting the CO2 to a carbonate. And this, in effect, natural somehow, because the carbonate that we are producing is the equivalent of the eggshell. When you have a chicken giving a birth to an egg, I have no clue if you have seen it, how it happens, but the egg, when it comes out from the chicken, it's really soft and it reacts extensively. It comes as a calcium carbonate, but very deficient in oxygen. And when it reacts with the oxygen of air, it becomes hard. And that same process, in effect, happens in the climate. I mean, carbonates are the core component of geoscience somehow. So I have no clue if I have explained myself very well or not, but well, I try to do my best. I'm sorry if I have not responded to your question, but it's not photocatalyst. It's not a catalysis effect. No, it's not a photocatalyst. It's not band gap engineering. No, it's not chemical atomic coordination. No, no, no. It's completely the opposite. And we followed the path.
Okay, thank
Go
you.
to Nature Scientific Report. I will send the presentation to Prof. Mérieux. Go, please. She can share it with you.
There's one more question over here from David. Okay, so my question is, when you are doing the process, so you identify the materials that have the properties of interest you want to solve the problems that you want to address, but theoretically, these materials have the properties you want, but at what point do you check for dynamical stability, for example, before you go into the lab to fabricate the materials?
It's the condition of somehow, if I may say, it's the boundary condition that you will impose that will define to you the way to go forward.
So it is specified early on in the process of search of these materials, right?
Yes.
Daniel, I have a question.
Daniel?
Hi, yes. Hello, Prof. Thanks for your presentation. I just have a simple question. I mean, so you're talking about something, doing research with AI and machine learning. What really caught my attention was the data centers. And I mean, it's all connected to these AIs and stuff. But then also earlier in your presentation, you talked about water scarcity. And we know now these data centers are a huge cause of water scarcity in a lot of places in the world. What's your ethical take on these two competing interests?
Well, what is sure is that indeed artificial intelligence, AI, will come with a cost, and that cost is water. You are absolutely right. Why? And that's why the UAE, other countries are going, are moving their data centers to other places. You take the UAE, going to the Mediterranean Sea, because I can say one simple solution, and the US are moving to Spain. The point is that, how can I say, you cannot use normal water, drinkable water, but the seawater. But seawater comes with a problem. Desalinization comes with a brine, and this brine is huge. It's a huge. You cannot put it back in the sea. It will increase the acidity, and so on and so on. So the unique way, the unique way, as much as I think, is that geoengineering of harvesting artificial rain is the way to go. You know that, how can I say, we can harvest the clouds, and Africa has a very large, extremely large coast. You have Africa, which is a border with the Indian Ocean, with the Mediterranean Sea, with the Red Sea, as well as with the Atlantic. And we might think for our own usage, think about cloud seeding and artificial rain harvesting, but not its usage for cloud, for data centers cooling. It is just massive. That is, we will have to make a choice: cloud data centers or drinkable water. But you are absolutely right. You're absolutely right. That is the snag that will put down the, how can I say, the data centers energy. In addition to the energy amount, the energy absorbed is huge. And that's why Amazon and Tesla, they are trying to go for nuclear, building their own nuclear reactors. So it will come with a price, but water is a major one.
Okay, just a follow. But isn't this in contrary to the UN development goals? I mean, if we have to choose between water and cooling data centers, I mean,
well,
are we going?
it is. You are right. We got you. You are absolutely right. The point is, how many of us, just here, how many of us, we remove our emails? We remove them from the cloud. Not much. All our emails are in the cloud. And the bulk of our data is in the cloud. The cloud, what does it mean? It's in the data center. If, how can I say, if each of us also can make an effort cleaning our, how can I say, portion in the cloud, we will make life easy. But I think there must be regulations and code of conduct, good governance and transparency in this. There is a lack of regulations, and that's why we should come with that. You are absolutely right. And well, the ones who are consuming a lot are the young generation. All of us are with TikTok, LinkedIn, what. So we have also to be responsible in that regard. But an ethical discussion must come in a way or another.
Okay, thanks.
Okay.
Thanks.
Thank you very much. Any more question in the room? Or no? Okay. So maybe we will close it for today. And Professor Maaza, we thank you immensely for giving a bit of your time for IFR and its community. And yeah, so thank you very much again.
Thank you. Thanks a lot.
Bye-bye, guys.
Bye-bye.
Bye-bye.